Hello everyone, welcome to Skilled Dev. Trey here, and in this lesson, we are going to solve Robot Maze. The prompt states you have a matrix that represents a maze through a room. You want to write a function that returns a Boolean true or false if there is a path to an exit. So in this maze, you always start at the top left, point 0, 0, and you can only move down or right. A 0 represents an open path, and a 1 represents a closed path. If you find a number 2, or you can reach one through the path from the top left to any point, then you return true. And if you can never find the number 2, which represents the exit, then you return false. So in this first example, when we start at the top left, we see that we can reach the number 2, which is in the bottom right. So we return true. With the other example, we start in the top left, but we can't reach this number 2 because when we go down, it's blocked by number 1, and 1s represent that you can't cross a path. So the path is blocked, and we can only move down and right, so there's no way to get to this point. So for this example, we return false. And what we'll see is that this problem is actually a classic example of backtracking. And we know with backtracking, there are 3 key components. The first is that there's a decision to make. So in this case, we can either go right or go down at any point to follow a path. There are constraints, and we'll really understand what this means a little more on the next slide. And finally, there's a goal. We follow our paths until we reach a successful answer, or if we find an ending point, we backtrack and make new decisions. So let's talk through what this means step by step. You first make a decision. So like I said, we can either go down or right to follow paths to eventually look for an exit. We're going to do this recursively. So we'll have a function that goes right and goes down, and then if you hit a terminating condition at the end of the path, your recursion will unwind to the last point that you had a decision to make. So then we unwind to this point, and then we just try the next decision or the next option. We do this for every possible option in the question. And then finally, we're done if we either calculate the solution or we exhaust all the possible choices that we can make. And I think one important thing to note is that we're intentionally generating all the possible options that are allowed within our constraints. So this might seem inefficient, but with many problems, this is actually the only path forward. It's the only way to solve them. And solving a maze is actually a classic example of backtracking, and the problem we're solving now is a modified version of a maze. With a maze, you have a decision where you can follow paths, so here we go right, down, left. We hit a terminating condition, so we backtrack, and then try the next path. And you keep trying these paths until you either hit a block, or you eventually reach the end, at which point you know the entire path through the maze. Another backtracking problem is solving a Sudoku board. And what you do is you just iterate through it and try all the possible numbers 1 through 9 at each point. However, we know with Sudoku boards there are strict constraints. So within any row, column, or subsquare, a number 1 through 9 can only appear once. So this limits the numbers we can try, and we only use numbers that haven't appeared in that row, column, or subsquare. So what we do is we iterate through the entire board, try all the possible numbers at each point within the constraints, and then finally, once we have iterated through all the points and making sure that they all fall within our constraints, we've solved the board. And finally, 8 queens is a classic backtracking problem as well, because what you do is you try to place 8 queens on a chessboard and put them in positions where they're not able to attack each other. So all you do is iterate through the entire board, and then at each point you place a queen, and then you iterate forward and try to place another queen. But you're under the constraint that you can only place a queen if any of the queens that are already on the board cannot attack a current spot. So now, let's apply the principles of backtracking to this question and see how we can solve this problem in an optimal way. So we have this board. We always start at the top left, the point 0, 0. Then we can only move right and down, and we're eventually looking for the number 2, which indicates an exit. Zeros indicate an open path, meaning we can follow them, and 1s represent a blocked path, which means we can't cross through that node. So now let's highlight the board to make it a little easier to visualize. This yellow point, 0, 0, is where we start. Then all the zeros are open paths. If we hit a 1, it's a blocked path. And when we find a 2, that means we found the exit and can return true. If we can't reach 2, then we return false. So one thing we may start to see is that there are many paths to get to 2. We only care that there's at least one path. If there's one or more paths, we return true. So if there are multiple paths, that means we'll cross through nodes multiple times. This is actually very inefficient. Let's see what this looks like. So there are many possible paths that cross through any given node. It would be very inefficient to every time we cross through a point, to follow all the paths from that point every time. We only care about what happens the first time, because obviously it's going to be the same result each time we go through a point. So here, if we go right, right, down, or right, down, right, we reach the same point. So once we reach this point, both times we hit it, we wouldn't want to go right, down, 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 right, right, down, down, and then again when we come through it, follow those same paths. So what we can do is use memoization to remember the results of going through a point. So at each point, we'll just remember if going through this point led to a successful ending or a blocked path. Then when we hit this point again, we just know if this point individually should return true or false. This is going to ensure that we touch each point at most one time. Once we know if the result of going through a point is successful or not, we don't need to follow any paths from that point again. So now let's block this path here to make it a little easier to see what's happening. So if we go right, right, down, and then we follow these right, it leads to an unsuccessful path. So then we backtrack, and we reach this point again. If instead of going right, we go down, now we have 2 decisions again. We can either go right or down. We saw that when we went right, we'll go to this point, and this point has already been visited. We also know that going through this point leads to a failed path. There's not a path that leads to a successful exit. So instead of continuing to follow these nodes to that blocked path, we store here that it returns false. So we don't follow that way again, we don't make that decision, so we just go down. We go down, down, and now we can go right or down again. Let's check the down path this time. We go down, then we can go right or down again. Down is blocked, so the only option is right. We go right, and now we have a decision to go right and down again. If we go down, we're blocked, we can't go right or down, so we backtrack. We get back to this point, and we must follow right. Once we're at this point, if we go down, it's blocked, but then if we go right, it's successful. So we return true, and then we propagate this true up. This was our last decision point. We would have already called our recursive function to go right, so we would go right. Then we would decide if we want to go right and down. We would check right again. This node has a block, but then it saw that this path is true. We would have stored in this node or memoized the result that it led to a true path, so we don't actually need to follow it. We can then just return true. We return to this point. It saw that both of these are true, we only needed to see that one was true, but either way, we return true from this function, and then eventually, this true value is going to propagate upward. We get back to our original function call, which returns true. So we're trying to determine that at least one path gets to the exit successfully, and if there is one or more, we return true. So we want to make sure we always propagate true values upward. So if either the down or the right path return true, we propagate this true up. Or if in this case, where we reached the end of this path, we saw that both the right and down couldn't be true, so we return false. But anytime we get to a point where at least one of its right or down decisions return true, we propagate that true. So we're memoizing if any path through a node returns true or false. If neither right or down can lead to the end, then this node is false. So both right and down are false, then the node is false. But if at least one of the right or down paths can lead to the exit, then this node is true. So if at least one is true, then we memoize this value to be true. So each cell in the matrix is a node, and from this node, we can either go right or we can go down. And what we're going to do is continue to follow these paths recursively until you reach the end of a path. If the path reaches an exit, the recursive function returns true, and then we continue to propagate that true value upward. Or if a path fails to reach an exit, it returns false, and then the recursive functions start to return false unless it merges with the path that returned true. So each node is going to call a function to go right and go down. Then once the recursive cases reach a base case or an end, they start to return the result from each function. Then each node waits on the down to return and the right to return. Then based on these return values, this node is going to decide what it should return. But in addition to that, we also memoize the solution. So once we get a result from the down and the right path, we decide what this node should return and then also store that result, so if we ever come through this node, we can just return immediately for any subsequent call. And there are only 4 possible states that this node can take on, so let's explore those. The first 2 states are when both recursive functions down and right both return true, or both recursive functions down and right both return false. If they both return true, then this node will be true, so we return true, and then memoize the value as true for this node. If they both return false, then this node returns false, and we memoize the value false as well. But then what if one path returns true and the other returns false? In both of these cases, the node is true because we only care if one path can reach the exit. So in both cases, we return true, and then we memoize the value as true for these nodes. And the way we're going to memoize the results is just by using a matrix that's the same dimensions as the input matrix. It's going to initially be empty, but then when we check a point, if the right and down return false, then this current point is false. If either the right or the down return true, then we set a point to true. Then, anytime we try to traverse through a point that already has a value, we just check the memo array to see if these paths return true or false. Then we can use this value at the point that was trying to go to it. So if we look at our input matrix again, obviously it's going to return true because we know there's a path to the exit. The red items are set to false in the memo array because those paths couldn't reach the exit. So when we go right and get to this point, since we can only go right and down, it's only possible to get to this blocked path. However, this point, even though it can go right and would reach the blocked path, its down path does return true, so we set this to true. Then we get down here, and all these points can reach the exit. So we'll only go through any single point once, and then set its value to true once we see a point has reached the exit, and the recursion starts to unwind. This point here is false, because once we move down, it can only go right and down, which does not lead to the exit. Since this point's right path can lead to the exit, at least one got there, so it's set to true, and these trues propagate upward until we get to the original function call. And finally, let's look at an extreme case where the board is entirely open, except the bottom points, so the exit is blocked. This is a good illustration of why we're memoizing the results of each path. Let's say we went all the way right, then down, and hit this point. It's going to be false, so we know anything that goes through these points will also be false. However, if we weren't memoizing, we would continue to go through the same paths. So we could go right, then down, then right, and follow these down again. And then right, then down, down, then right, then down, and it's false again. So even though all these would be false the first time we go through them, if we don't memoize, we will continue to check the same paths through points we've already visited. However, if we set all these as false the first time we went through them, we would only touch the points once. We would never try to go right through these again, or we would never try to go right and then down through this again. So by using this matrix that's the same size as our input, we can memoize the results, which adds O of n space, but then ensures we just touch each item once, so we'll at most touch all n items one time. So now that we have the intuition, let's walk through the solution. We're going to recursively walk right and down, which allows us to check all the possible paths. There are 3 base cases. We reach the edge of a matrix. This is false, meaning we didn't find the exit. We reach the exit. This returns true. Or we reach a blocked node. This is one of those 1 values. We return false. For the recursive case, we're going to move down and right, and we're going to return true if either of the paths ever reach the exit or reach a node that has reached the exit and shows true. Otherwise, we return false. So if both right and down return false, then this current node is false. We're going to memoize the results for the recursive case for each node the first time we visit it, and then anytime we try to pass through that node again, we just use the memoize value and return that. This prevents going through the same node more than once. The time and space complexity are both R times C, where R is the number of rows and C is the number of columns. So we could also say that time complexity is O of n, and O of n, where we touch all the nodes at most once, and we're using a memoization data structure to store all n items. And now we're ready to write the solution function hasExitPath. We know we have numbers within the problem that indicate the paths we can use. A 0 indicates an open path. A 1 indicates a blocked path. And a 2 represents the exit. So let's first define these in constants to make our code more readable. Now we just want to check that we're given a valid input. If we don't have a valid input, then there can be no exit, so we return false. We're also going to create a matrix with the same dimensions as the room or the input matrix, and we use this to memoize if any given point can reach the exit. Now we're going to create a recursive helper function to traverse through the room. We pass it the room input matrix, the point 0, 0, or the row and column for where we start, which is the top left at 0, 0. And then we pass it the memoization matrix. Now let's actually define this function and implement it. So we define the function that takes the input, and then the current row and column index that we're at. We also continue to pass it the memoization matrix so we can check those memoized values and then also add to it as we follow new paths. Now we check the first base case, and we want to see if we're still inside the matrix, or still inside this room. If the row is greater than the row length, or the column is greater than the column length, we're outside the room. If we reach the edge of the matrix, then we know this isn't a successful path, so this current path returns false, because we are no longer in a cell and the path going this direction is no longer valid outside of the input dimensions. Now we've reached the second base case. We want to check if the current node is a valid path. So if we memoize the current node as being a valid path, or if we've actually reached the exit node, both of these then indicate we're on a successful path, so we want to return this upward. Since we know it's successful, we memoize this point as true. Then we also return true to propagate this to the recursive calls. And finally, we reach the third base case, where we reach an invalid node. It's invalid if we already memoized this value to be false, so if the full path going through this node can't reach the exit, or if we reached a blocking node. If it's not a valid path, or we reached a blocking node, we add it to our memoization matrix as false, and then we return false to propagate upward to the recursive calls. If we haven't hit a base case, then we continue to traverse down and right. We traverse down by incrementing the row, so row plus 1, and we stay in the same column. Then we traverse right by staying in the same row and incrementing the column. Now we want to check the result from both the down and the right. If they're both false, then we know this path can't lead to an exit. Otherwise, this must mean at least one of those is true. If one is true, we know this path is true, so we set the current row and column to true. And finally, we return the results. If either one of these is true, the OR short circuit operator will return the true value. So if down result is true, it just immediately returns this. If down result is false, it will return whatever is in right result. So if right result is true, it returns true. Or if right result is false, that means they're both false, and then this overall returns false. And finally, we return the result from all the recursive calls as our solution. We run the code and the tests pass. So in this question, we traversed through a matrix, but we realized there were many paths to look for an exit node. So in order to preserve the time complexity, we memoized the result of going through every path, so then we touch each node at most one time. Thanks everyone, and I'll see you in the next lesson.